Welcome to the deep dive. Ever wonder why, say, table salt is this hard little crystal, but the copper wire in your phone charger is, bendable
Yeah.
and conducts electricity?
Or why water dissolves salt, but maybe not oil. Yeah.
Exactly. It all comes down to something invisible, chemical bonds. So today, we're taking a deep dive into these forces, the ones holding the physical world together at the atomic level.
Right. And we're basing this on a really helpful tutorial about chemical bonds.
Yeah.
Our goal isn't just to, list the different types. We want to really unpack how atoms connect and, maybe more importantly, understand why that connection dictates the properties of, well, pretty much everything you touch and see.
Yeah, think of it like a key. Understanding bonds gives you this shortcut to figuring out why materials act the way they do.
It kind of feels like a superpower almost. Learning how these tiny atomic decisions about electrons decide if something's going to be, I don't know, a gas or a brittle solid or maybe a shiny conductor.
Okay, so let's get into it. The core idea from the source material is pretty clear. A material's properties. They're basically set by the chemical bonds holding its atoms together.
And the tutorial really focuses on the three main players: ionic, covalent, and metallic bonds.
And it all kicks off with electrons.
Right.
Specifically the ones on the outer edge of the atoms.
Precisely. Those valence electrons. How atoms handle those electrons when they interact with other atoms. That's what determines the bond type.
They're all striving for stability, aren't they? Like getting a full outer shell of electrons.
Yeah, that's the driving force. How they achieve that stability together dictates the bond.
Okay, so let's tackle the first type the source covers, ionic bonds, described as involving electron transfer.
Yes, typically this happens between a metal atom and a nonmetal atom. Metals, you see, tend to give up their outer electrons relatively easily.
And nonmetals are kind of electron hungry. They want to gain them.
Exactly. So you get this movement, this transfer of one or more electrons from the metal to the nonmetal.
Which creates ions, right? Charged particles. The metal loses electrons, becomes positification.
And the nonmetal gains them, becomes negative and anion.
So what is the bond then? Is it like a string holding them?
Good question. No, it's not a physical link in that sense. It's the electrostatic attraction. Purely the pull between that positive charge and that negative charge.
Like tiny, really strong magnets clicking together.
That's a great way to picture it, snapping together in a very specific ordered pattern. A crystal lattice.
Okay, so that strong attraction.
Yeah.
That must be why ionic compounds generally have high melting and boiling points, like the source mentions.
Absolutely. You need a lot of heat energy to overcome that strong electrostatic pull and get those ions moving freely, to melt or boil.
Right. Makes sense. Now, conductivity is interesting. The source says they only conduct electricity when dissolved or molten, not when solid.
Correct. Think about that crystal lattice we mentioned. In the solid state, those positive and negative ions are locked rigidly in place.
So even though they're charged, they can't move?
Exactly. They can't move to carry an electrical current. But if you melt the compound or dissolve it in, say, water,
then the ions break free from the lattice.
Precisely. They become mobile. Then they can move in response to an electric field and carry charge. That's when they conduct.
Got it. Dissolved or molten. The source also notes they often dissolve in water, form those crystals, and are brittle.
And that brittleness ties back to the lattice, too. Imagine trying to slide one layer of ions past another in that rigid structure.
Yeah.
You'd eventually line up positive ions next to positive ions and negative next to negative. They'd repel strongly.
Then crack, it shatters.
Exactly. Brittleness.
The classic example, the tutorial uses sodium chloride, right?
Yeah.
NaCl, table salt.
Perfect example.
Yeah.
Sodium, a metal,
Yeah.
happily gives an electron to chlorine, a nonmetal. You get Na+ and Ki minus ions.
Which attract and form that cubic crystal we all know.
And these ionic compounds are everywhere using these properties. Obviously, table salt for seasoning.
Baking soda, not Cheetos. Used in cooking, cleaning, dissolves easily.
Calcium chloride, K-clay for de-icing roads. It dissolves in water, releases ions, and messes with the freezing point.
Lowers it.
Lowers it, yeah. And think about lithium compounds in batteries relies on those moving lithium ions. Or fluoride in toothpaste.
Strengthening teeth enamel. Okay, so that's ionic. Electron transfer, strong plus attraction, resulting in those specific properties.
Got it.
Now let's switch gears. Covalent bonds. The source describes this as electron sharing.
Right. This is typically what happens between two nonmetal atoms. Instead of a giveaway, they find stability by sharing pairs of valence electrons.
So the electrons orbit both nuclei, essentially.
In a way, yes. They occupy a region of space between the two atoms, and it's the shared electron pair, or pairs, that holds the atoms together. That is the covalent bond.
And the source mentions different types based on pairs. Single, double, triple.
Yeah. One shared pair is a single bond, two pairs is a double bond, three pairs is a triple bond, like in nitrogen gas and euros. Very strong triple bond.
And property-wise, how do these compare to ionic? The source says variable melting points, often lower.
Generally, yes. Much lower than typical ionic compounds and quite variable. Also, they're usually poor electrical conductors.
Okay, wait. Why the lower melting point? If the bond holds atoms together.
Ah, good point. It's because covalent bonds often form discrete molecules. Think of water, HO. The covalent bonds within the molecule, holding the H to the O, are strong.
Right.
But the forces between separate water molecules are much weaker, things like hydrogen bonds or van der Waals forces.
Okay.
So when you melt ice or boil water, you're not breaking the strong OH covalent bonds inside the molecules. You're just overcoming those weaker forces between the molecules, letting them move apart.
Ah, I see. You're separating molecules, not breaking atoms apart within them. That's a crucial difference.
Huge difference. And that explains the generally lower melting and boiling points compared to ripping apart that strong ionic lattice.
And the poo connectivity.
Well, the electrons are pretty much locked into those shared bonds between specific atoms. They aren't free to just roam through the material and carry charge, like we'll see in metals or like the ions in a salt solution.
Makes sense. Localized electrons.
Yeah.
The source also says they can dissolve in nonpolar solvents and exist as gases, liquids, or solids.
All true. Depends on the molecule size, shape, and those intermolecular forces.
Water, HOO, is the tutorial's key example for sharing, right? Oxygen sharing with two hydrogens.
Yep. And water is also a fantastic example of polar covalent bonds. The sharing isn't perfectly equal. Oxygen pulls the electrons a bit closer.
Giving it slight charges, which makes it such a good solvent for ionic things, for example.
Exactly. Its polarity is key. The source also gives examples like hydrogen gas, HRO with a single bond, oxygen gas, OO, double bond, nitrogen gas, NRO, that triple bond we mentioned.
And real-world covalent compounds, I mean, they're basically everywhere.
Everywhere. Life is built on them. Water, obviously.
Carbon dioxide,
Right,
Kaguro,
yeah.
photosynthesis, fizzy drinks.
Methane, CHR, natural gas. Plastics. Huge long chains, polymers, all held together by covalent bonds.
DNA itself, the instructions for life stored in a molecule built with covalent bonds.
It's fundamental. Now, here's something cool the source doesn't explicitly dive deep into, but it shows the power of structure within covalent bonding. Think about diamond and graphite.
Both pure carbon.
Both pure carbon, both covalently bonded, but diamond is incredibly hard, used for cutting tools. Graphite is soft, flaky, used in pencils. Why?
It's the arrangement.
Totally the arrangement. In diamond, each carbon atom is bonded to 4 others in this super rigid 3D tetrahedral network. It's like one giant molecule. To break it, you have to break those strong covalent bonds.
Okay.
In graphite, carbons form layers of hexagons. Within each layer, strong covalent bonds, but between the layers, much weaker forces.
So the layers can slide past each other easily.
Exactly. That's why it's soft and works as a lubricant or in pencils. Same atoms, same type of bond, covalent but different structure leads to vastly different properties.
That's a brilliant illustration. Okay, structure matters. Let's move to the third type from our source. Metallic bonds.
All right. This one is unique to metals. The tutorial uses the term electron C model.
Electron C. Sounds fluid.
It kind of is. In a metal, the atoms don't hold onto their valence electrons very tightly, and they don't share them in neat pairs like in covalent bonds either.
So what happens to them?
They sort of detach. The valence electrons are released by the individual metal atoms and become delocalized. They're free to move throughout the entire piece of metal.
Like a communal pool of electrons.
Exactly, a sea of mobile electrons. And what's left behind are the positive metal ions, the atom cores, basically.
Okay, so you have positive ions sitting in this sea of negative electrons.
Yeah. And the metallic bond is the attraction between those positive metal cores and this surrounding, mobile, negatively charged electron sea. It holds the whole structure together.
What strikes you most about this model, how it explains things?
For me, it's how perfectly it explains the classic properties of metals, that sea of mobile electrons. That's why metals are such fantastic electrical conductors.
Because the electrons can just flow easily when you apply a voltage.
Precisely. They carry the charge right through the material. Same for thermal conductivity. Those mobile electrons are great at transferring kinetic energy, which is heat.
Okay, that makes sense. What about being malleable and ductile? Hammering into sheets, drawing into wires.
That's the electron sea again. Imagine pushing on the metal. The layers of positive ions can slide past each other.
Without breaking the bonds.
Right, because the mobile electron sea just flows and readjusts around the new positions of the ions. It's like ball bearings moving in grease. They can shift, but they stay held together by the grease, the electron sea, unlike the rigid ionic lattice that shatters.
That's a good analogy. And the shininess, the metallic luster.
That's the free electrons interacting with light. They absorb and re-emit photons efficiently across the visible spectrum, making the surface appear shiny.
Okay. The source also mentions variable melting points and that metals form alloys easily.
Yes, melting points vary quite a bit depending on the metal. And alloys are essentially just mixtures of different metal atoms sharing that same electron sea. It accommodates different types of positive ions pretty well.
So the mental image is just positive metal ions bathed in this cloud of constantly moving electrons.
That's the essence of it. And metals built this way are just crucial for, well, everything technical. Iron, usually as steel for construction strong, can be shaped.
Copper for wiring, fantastic conductivity.
Aluminum for lightweight things, planes, cans, malleable, not too dense.
Gold for jewelry, sure, but also electronics because it resists corrosion and conducts well.
Definitely. And things like titanium alloys and aerospace strong, light, resists heat and corrosion. All these properties come directly from that electron-sea bonding.
So, okay, we've got the three main types. Ionic, with electron transfer and that strong plus-pin pole. Covalent, sharing electrons, forming distinct molecules or sometimes huge networks. And metallic, with that delocalized sea of electrons holding positive ions together.
Exactly. And the comparison table in the tutorial really helps crystallize the key differences.
Let's just recap that quickly. Formation, transfer versus sharing versus electron sea.
Yeah, conductivity. Only when dissolved molten for ionic, generally poor for covalent, excellent for metallic.
Melting point. Generally high for ionic, variable, often lower for covalent molecules, but very high for networks like diamond, variable for metallic.
Solubility. Often water-soluble for ionic, depends on polarity for covalent, generally insoluble for metals.
And the feel of them, the mechanical properties. Brittle ionic crystals.
Variable covalent, soft wax to hard diamond.
And that key malleability and ductility in metals.
It really does all trace back to how those outer electrons are handled, doesn't it?
It's amazing that one factor transfer, share or swim freely, determines if you get salt, plastic, or copper wire.
It shapes the properties of everything you use, constantly. Understanding the bonding. It really is that shortcut to grasping why materials are the way they are.
So we've seen the big three, ionic, covalent, metallic, how they differ based on electron behavior, and how that creates the just incredible variety of materials we see.
And the main takeaway, straight from our source material, chemical bonds dictate material properties. Understanding them helps explain so much of the everyday world.
So let's leave you with this thought, adapted from the tutorial summary. Chemical bonding is fundamental. The way atoms bond determines everything from the hardness of diamond to the conductivity of copper wire. Think about that. Keep exploring and questioning how the molecular world shapes our daily experiences. What are you noticing differently now about the materials around you?